Bismillah ar-Rahman ar-Rahim. Welcome to Tahar Scholar. We are الاثنين 29 أبريل 2024 بالجزائر, or in English, Monday, the 29th April 2024. So this is the first practical for chapter 2, and it is dedicated to Cramer's rule. So we have already studied in 4 lectures Cramer's rule and the Adjugate Matrix, and we have also done a tutorial, 2 exercises on this topic, on this first part of chapter 2. The practical will be subdivided in 4 parts. In the first part, we study how to implement Cramer's rule, and then the Adjugate Matrix in order to calculate the solution using the inverse matrix. And then we will apply the Adjugate Matrix, and we will see its advantage when you have the same matrix but with different images. So different systems to solve, but having the same matrix, the same linear mapping. And we apply that in a project Geom, in a simple project in geometry in 2 dimensions, I mean. And then we study the time complexity, both Cramer's rule and Adjugate Matrix. They are actually the same. They have the same performance and the same accuracy. Not as I said in the last video, in the tutorials, that Cramer's rule is more efficient actually. No, they have actually exactly the same time complexity. They are equivalent actually. But when you have several images, the Adjugate Matrix is far better. We will see that in detail in this practical. So let us first begin with Cramer's rule. So Cramer's rule we want to implement a function. We give to this function the matrix A of the system in RMM. We limit our function to m equal 2 or m equal 3. Because we said that both Cramer's rule and the Adjugate Matrix are inefficient, are impractical when the size of the system is large. And we need also to give as input, so first of all the matrix and the image vector B. And this is the input. What is our output? Is the solution, of course, X. And beside X, it could happen that the matrix we have given to our function is singular, is not invertible. In that case, we need also the rank. If the matrix is invertible, the rank is equal to m, is equal to the size of the system, and also the determinant. And as you will see, L and D are byproducts of the method. They will not involve more calculation or efforts. They are just a byproduct of the technique. So L is the rank of the matrix, and D is the determinant. And X is the solution, of course. So this is the output. Let's write it, but here the solution, and here the image. And the function should give it a name. We have called it solve lin system. Means solve a linear system using Gabriel Cramer method, GC. GC means Gabriel Cramer method. This is the first version. The second version, we'll use the Adjugate Matrix. Let's remember what is Cramer's rule. So Cramer's rule says that each component of the solution is equal to the determinant of the matrix A with vector B, the image, at the ith column. So we take the matrix, the mother matrix, for example 3 by 3, and we replace each column by a vector B. So for example, for the second component, for I equal 2, this should be the vector B, not the second column of the matrix A. And we calculate its determinant. This will give us the auxiliary determinant number 2. And as I said, we work only for matrices of 3 by 3 or 2 by 2. So here, for example, I equal 1, we get the determinant delta 1. This should be the vector B. This is for the case m equal 1, m equal 3, and this is for the case m equal 2. So, and we divide by the determinant of A. So our algorithm, this is the method, Cramer's rule. We have seen that, I think, in lecture 3, and the Adjugate Matrix in lecture 4. Cramer's rule. So our algorithm is very simple. We just implement the formula. Algorithm. So our algorithm, we first calculate delta 1, delta, the determinant of the mother matrix, by definition, and then we calculate delta 1, delta 2, and delta 3 in case m equal 3, or delta 1, delta 2 in case m equal 2. And then we check if delta is close to 0. If it is close to 0, to number 0, then the rank of the matrix is either 2 or 1. It cannot be equal to 3. And how we calculate it? We use the minus. If one minor, for example, in case m equal 3, we have 3 minors. If one minor is different from 0, then the rank equal to. Otherwise it is equal to 1. Because we have either 1 or 2. We don't have L equals 0. It's impossible. The rank is the maximum number of columns in the matrix that are linearly independent. You can't have a rank equals 0. It has no meaning. So it is either L equal 1 or L equal 2, depending of the minors that we have calculated, that we have computed to calculate the determinant. So we have already calculated the minors. We don't have to recalculate them. So it's just check, a very simple check to find out whether L equal 2 or L equal 1. This is for case m equal 3. For case For case m equal 2, if delta is close to 0, then L equal 1, because here m equal 2. And L cannot be equal to because the matrix is singular. Then it is equal 1. We have only two cases, L equal 2 or L equal 1. So L equal 1. So it's very simple in this case. We don't need the minus here. Minor here is an element, so minor of matrix 2 by 2, the minor is the element, is one element of the matrix. So we don't have to calculate further minus. So m equal 2. And finally, we calculate the solution. It's either delta 1, delta 2, delta 3 in a vector over the determinant of the mother matrix. So we put the auxiliary determinants in a column vector and we divide by delta in case m equals 3. Otherwise x equal delta 1, delta 2 in case, because we have only two cases. We have limited our algorithm to only two cases, m equal 3 or m equal 2. So in the case m equal 2, same procedure, we put the auxiliary determinants in a vector and we divide by the determinant of the mother matrix. So this is the case m equal 2. And that's it. So this is the algorithm with the important limitation. We deal only, so let's write it here. Deals only with m either equal to 2 or m equal to 3. And that's it. We calculate the determinant of the mother matrix, then the auxiliary determinants. We check the case where the matrix is singular to find out its rank using the minus, and finally we calculate the solution. Let's see this implementation on the computer. Let's go to our computer setting. So this is our function, Solin system Gabriel Cramer, and this is the file, the same name as the function. We take as input, as I said, A and B, the matrix and the image vector, and the tolerance. The tolerance to check whether a number is equal to 0 or not. Any number in its absolute value less than the tolerance is 0. And we take by default the value 100 times APS, like we have did actually in previous practicals in chapter 1 and in the crash course programming with MATLAB. And we get as a result, as an output, the solution, the rank, and the determinant. Let's read the comment. Solve a small system of linear equations using Gabriel Cramer's method, Gabriel 1704 till 1752 CE. CE means current era. Tahar Scholar Channel, module Numerical Methods as a first course, chapter 2, Systems of Linear Equations, implemented by Tahar Jawad, Tuesday, the 6th February 2024, in Baida, Algeria. And I revised it the 20th April 2024. The input AB tolerance and the output XLT. So the first thing we do, we check whether A is a square matrix. We use function is square. It's equivalent to check size of A first dimension is equal size of A second dimension. That is the number of rows equal the number of columns. It's the same. And then we check whether there are as many rows in the matrix as there are elements in vector B. The number of rows must be equal to the number of elements in B. Then we check, this is very simple, check for consistency, for size consistency. And then, as I said, we have limited our algorithm to only 2 by 2 or 3 by 3, matrices of 2 by 2 or 3 by 3. We check that, otherwise we display an error message. The first thing we do, we initialize the M to the size of the matrix, of the system, or the number of rows, the number of columns, and the rank by default is equal to M. If the matrix is singular, we change that value, and X is empty. So an empty vector means X is empty. Calculate, first thing to do, we calculate the determinant and the rank. So this is case 2. We switch, we have two cases, case 2 or case 3. In case 2, we have a matrix 2 by 2. We calculate its determinant, the formula of the determinant. Very simple. And then we check whether it is equal to 0 or not. If it is less than the tolerance, its absolute value is less than the tolerance, then the rank equal 1. It cannot be equal to. And we return. We do not have to calculate. There is no solution. The determinant is equal 0, close to 0. The matrix is singular, we return. Otherwise we calculate the auxiliary determinant using the vector B. And we put the two auxiliary, D1 and D2, in a column vector. We have called it D. So D contains the auxiliary determinants. We do the same with rank equal 3, but here more calculation. So we start with the minors of the first row, M11, first row, first element, second, third element. We calculate the minor by eliminating the first row and the first column or second column or third column, depending on the minor. And then we calculate the determinant. The minors, M11, M12, and M13, and the elements, the corresponding element. And the sign alternates between plus, minus, and then plus. If the determinant, its absolute value, is less than the tolerance, then we check whether at least one of these minors, of these three minors, is different from 0. If it's the case, then L equal 2. Otherwise, L equal 1. Once this test is passed, it means that the matrix is invertible. If not, of course, we return. But if the matrix is invertible, there are 9 minors, to calculate the auxiliary determinants. We calculate them by columns. The first column, the second column, and the third column. The first element of each column, we have already calculated them. M11 is the first element of the first column, the minors of the first column, and M12 of the second column, and M13 of the third column. And we use these these 9 minors to calculate the auxiliary determinants. And we put them, like we did here in M equal 2, we put them in a column vector. And then finally, we calculate the solution. We just divide the column vector containing the auxiliary determinants by D. Now let's go to the script where we test our function. We called it proj sol linear system. Means project that tests the function sol linear system. Let's read the command. Solving a given system of linear equations using Cramer's method. TAR Scholar Channel, Numerical Methods as a First Course, Chapter 2, Systems of Linear Equations. By Tahar Jawad, Tuesday the 6th February 2024, Ain Baida, Algeria. Ain Baida is my hometown where I live currently. I was born here. So we clear all as usual and clear the console. And then we choose among a sample of systems of linear equations using switch and input. We ask the user to input a number, and according to that number, we select, the system, the matrix, and B. That defines our system. So we have already done that in lecture 3, the first and the second system. case 3, case 4, case 5, and case 6 are from the tutorials. Same systems we have presented in tutorials. And in case 7 and case 8, I have here two matrices that are singular. The first has rank equal 2, and the second has rank equal 1. The second is the inner product of a column vector with a row vector. That's 3 by 1, and this one is 1 by 3. We get a matrix 3 by 3. But each column is the same vector u, but scaled by an element of vector v. So the rank is equal 1. And we have chosen it randomly. I added these two systems to check the part of the code where we calculate the rank. That is this one and this one. It's important to check every part of the code. It's very important. There is a golden rule that states a non-tested code is a broken code. Always test your code, all parts of the code. So we added these two systems to just test the rank of a matrix. Then we print the system using num2string and printf, and then we call our function linear system Gabriel Cramer, a and b, the tolerance the default value, and we get xld. If L equal the rank equal the size of the matrix equal the number of rows or the number of columns, then we have the solution. We print it, we print the determinant, and we check the residual. This is the residual. ax minus b. ax minus b. A times x is the approximate image, and b is the true image. We calculate the vector, the difference between these two vectors, and then we calculate its norm. If its norm is close to 0, then the residual is close to 0. Otherwise, we don't have to display the whole vector. We just calculate its norm and display it. If the norm is close to 0, then everything is fine. We have the solution with good accuracy. Otherwise there is a problem in our algorithm. And of course, there are no problems, but always check. Always check. Otherwise, if L is not equal to the size of the matrix, then it is a singular matrix. The determinant is close to 0. We display the rank. We don't have to display the determinant because it is close to 0. We display the rank. It is equal to 2 or 1 in case m equal 3, and it is equal to 1 in case m equal 2. And that's it, very simple. We prepare data, as usual, we prepare data, then we call our algorithm, and we display the results. Like we have done that several times in practicals. So let's check it. Let's run it. So let's check the first system number 1, and type enter. As you can see here, this is the matrix A, and this is the vector B, and this is the solution. And you can see the determinant, the value 2.89. You can check the lecture number 2, or lecture number 3, or lecture number 4, where we have introduced Cramer's rule and Adjugate Matrix. We have already calculated that by a calculator. You can check. And the residual is almost equal to 0. So it's okay. Let's do the second. The same. The matrix, the vector B, the solution, the determinant, and the auxiliary is close to 0. Number 3, this is from exercise number 1. We have already calculated these values. The determinant, the norm of the residual is very close to 0. And let's not test 4, 5, 6, 7. For sake of time, let's go to number 7, where the matrix is singular. Here the matrix is singular, so we display the message singular matrix and the rank equal 2. So when two columns are linearly independent, and the dimension of the image space equal to its plane. And then let's check number 8. Number 8, as you can see, it's the same vector 0, 1, 0, 2, 0, 3 in the first column, the same in the second column, but scaled, multiplied by 2, and here multiplied by 3. So it's the same column. They are dependent, all. So the rank must be equal to 1. And as displayed here, rank equal 1. So that's it for Cramer's rule. Let's move to the second part, the Adjugate Matrix. The second part of this practical is dedicated to the Adjugate Matrix. So first of all, let us make a simple revision of the method. The Adjugate Matrix of A is defined as the transpose of the cofactors of the elements of A. So each element ij of the adjugate is the cofactor, by definition, is the cofactor of a ji, not ij. Okay? And the cofactor is the sign with a minor. So minus 1 to the power of I plus j. So here the sign here is either plus or minus depending of the exponent, depending of the row index and the column index, times the minor mji. Okay, this is the definition. And we use that to calculate the inverse. We have proved the theorem that the inverse matrix is actually the inverse of the determinant of A, an invertible matrix, of course, otherwise the inverse doesn't exist, times the adjugate matrix, the adjugate of A. And we use that to calculate the solution, namely X equal the inverse matrix dot the vector image B. So the advantage, this is the solution. The advantage when you compare it with Cramer's rule, the adjugate matrix is independent of B. The adjugate matrix is independent of B. So you could have the same system, the same matrix, I mean different systems, the systems are different, but the same matrix, they have the same matrix A. And they are different because the image is different. So you could have a scenario where you have, for example, the matrix A dot the vector X 1, big X 1, and you have the first image big B1, and then you have to calculate the vector X number 1, and the same system, the same matrix, I mean, but with a different image B2. You have to find another solution because the image vector has changed. So you have to look for another solution, and so on. Let's say we have a set of n images, and you have to look at each system for the solution corresponding to each image. So if we use Cramer's rule, we have to calculate the auxiliary determinants for each system, because the auxiliary determinants depends not only of A, they depend also of the vector image. You have to replace the vector image in one of the columns of A and calculate its determinant. the auxiliary determinants in Cramer's rule. In Cramer's rule, the auxiliary determinants depend on the vector image. So when you compare that with the adjugate matrix, the adjugate matrix is independent of the image vector. So when you have several images, you calculate the adjugate only once, the adjugate matrix only once. That's the main advantage. So when you have a scenario where there are several images, the adjugate matrix, the method using the adjugate matrix is the right method. There is no comparison. But when there is only one image, you can either choose Cramer's rule or the adjugate matrix. They are equivalent. They have exactly the same time complexity. As we will see, we will revise that at the end of this practical. So let's rewrite our systems in this form. The same matrix, a matrix X. A matrix X contain all the solutions by column. So it contains x1 and x2, x3 till xn. All the solution for these systems. And the image vector is stored by column also in a matrix B. So B1 will give us x1, B2, B3, etc. till Bn. The same number of columns in X and B. And our goal is to find the matrix X. So when you have this scenario, the adjugate matrix is the method to choose. So our goal in this practical is to implement a function that solves this system. So this is the method. Now let's see the input-output. The input-output, we have the matrix A of the system. We need the matrix containing the images. So let's write the set of images stored by columns, and the tolerance. So this is the input. And the output would be a matrix X, the set of source vectors also stored by columns. And of course, when the matrix A is singular, we need the rank and the determinant, like Cramer's rule. So the rank and the determinant. They do not involve further calculation or byproducts of the method. So this is the output. So the only difference in the input-output is that here we have several images and hence several sources. So this is the output. And let's call our function Sol linear system adjugate instead of Gabriel Cramer. So the same name, similar, I mean, to Cramer's rule, but here we have added Adj, the version of Adj. Okay, and let's see briefly. The algorithm is very simple in this method. So what we do, first of all, we calculate the determinant, which is by definition the determinant of A. So D, we calculate the determinant, and then we check whether the matrix is invertible or not. So if the absolute value of D is less than or equal the tolerance, it means that D is close to 0. And hence A is singular, and we compute the rank using the minors method, like we have done with Cramer's rule, using the minors method. The minors we have already calculated when we calculate the determinant. So no extra effort. And these two steps are exactly the same, as in Cramer's rule. Okay, and then the adjugate matrix. There are two cases, m equal 2, and here also, of course, we limit the size of our matrix to 2 or 2 by 2 or 3 by 3. Yes, m equal 3. So for the adjugate matrix, here is very simple. You do not even have to calculate the minors. The minors are the elements of the matrix. So we just swap the two elements in the diagonal. Here A22 becomes A22, and here A11. A11 was here, it becomes here, and vice versa. So here we just swap the two elements. And for the two others, here first row, second column, we add minus. And here the second row, first column, we add minus. And that's it. And for the adjugate matrix, here we have to calculate the minus by columns, as we have done in lecture 4 and in tutorial exercise 2. So what we do here, we have 3 columns, but the first element of each column has been already calculated in the determinant. So we calculate the first column. Let's write M1, 2, and 3, first column. But this term has already been calculated when we calculate the determinant. And the minor 1, 2, 3 of the second column, same, is already calculated has been already calculated when we calculate the determinant. And the third column, 1, 2, 3 of the third column. Same here. So these 3 already computed in step 1. Okay, when we calculate the determinant. So we have to calculate 6 minus and put them in the adjugate matrix by row, because it's the transpose of the cofactors. And the cofactor also, you have to care about the sign. So let's write like that. You have to care about the sign. Here plus I equal 1 and j equal 1. So it's plus. And then it alternate. I equal 1 and j equal 2. 1 plus 2 is 3. So it's an odd number. To the power minus 1 to the power of 3 is minus 1, is minus. So plus, minus, plus, minus, plus, plus, minus, minus, plus. It alternates. And then we put the minus. The first, the second, the third of the first column. And the first, the second, the third of the second column. And the first, the second, and the third of the third column. And that's it. By definition. And once we have the adjugate matrix, we can calculate the solution. Very simple. Instead of writing x1 equal 1 over the determinant of A times the adjugate of A dot vector B1, and x2 same times adjugate of A dot B2, etc. till the nth solution, same, the inverse of the determinant, times the adjugate of A dot Bn. Instead of writing like that, we can compact them in one single matrix because we have put the images by columns in matrix B, and the solution same by columns in matrix X. We can write this is equivalent to write the matrix X containing all the solution is the inverse of the determinant of A times the adjugate of A, which we have calculated in the previous step, times dot the matrix B. So here, for example, 3 by 3, when we have a matrix 3 by 3, and we have, for example, 5 images, so we have 3 by 5, 3 by 3. Then we should have also here 3 by 5. And for each image, for example, the second image corresponds the second solution. So just product of two matrices. While in Cramer's rule, because the auxiliary determinants depend on B, as I explained before, you have to calculate for each image a set of auxiliary determinants and recompute them again with the second image and so on. While here you calculate the adjugate matrix independently of the image, only once. And then you calculate the solution by simply using the inner product. And that's it. Let's see the implementation of this algorithm on the computer setting. So our function, Sol linear system with the adjugate matrix, all the inverse matrix. So as you can see here, the same name of the file and the function. We have as input A and B, and the tolerance. B contains the images by columns, and as output XLD, big X, is a matrix containing the answer of the system or the source vectors by columns corresponding to the images given as input. So let's read here, solve the comment, solve a small system of linear equations using the Adjugate matrix. Here we look for the source vectors of a set of images, of a set of image vectors using the same linear mapping defined by matrix A. The image vectors are stored by columns in matrix B, and their corresponding source vectors are stored also by columns in matrix X. Exactly what I have already explained. Tahar Scholar Channel, Module Numerical Methods as a first course, Chapter 2, Systems of Linear Equations, implemented by Tahar Jouad, Tuesday, the 20th April 2024, Ain Baida, Algeria. And the input AB tolerance XL and D. So this is the first time actually I implement the Adjugate matrix, because I used to think that the efficient way to solve small matrices of 2 by 2 or 3 by 3 is Cramer's rule. And calculating the inverse of a matrix is always inefficient. But that's not true. That's not true. Actually, as we will see later in this practical, and we will see that also in the implementation, that calculating the Adjugate matrix or the auxiliary determinants involves exactly the same amount of calculation. So the two methods are equivalent. But the advantage here is that you can deal with a set of images, which is, of course, not efficient with Cramer's rule. As I explained, the auxiliary determinants depend on the images. So you have to recompute them for each image. Let's see, it's very similar to Cramer's rule. Very similar. Exactly, first steps are exactly the same. So we test if the matrix is square. The number of rows in matrix A must be equal to the number of rows in matrix B. The number of columns in B, of course, doesn't matter. 1, 2, or more. And suitable only for small matrices. Otherwise, we display an error message. We initialize M to the size of the matrix, the rank to equal to M. If the matrix is singular, we recalculate it. And X to be empty. It has exactly the same size as X will have exactly the same size as matrix B. In the case where matrix A is invertible. So we calculate the rank, the determinant and the rank. If the determinant is close to 0, the rank equal 1. Exactly, as you can see here, exactly the same steps we have done with Cramer's rule. And then we calculate the Adjugate matrix. No auxiliary determinants here. And the Adjugate matrix depends only on the matrix A. We swap the elements on the diagonal and we add the sign minus in the case M equal 2. In the case M equal 3, we calculate the minus of the first row, then the determinant, and then in the case the determinant is close to 0, we calculate the rank by checking the minors. If at least 1 is different from 0, then the rank equals 2. Otherwise, the rank equals 1. Exactly the same as Cramer's rule. Exactly the same. And then we calculate the minors by columns and we put them in the Adjugate matrix and taking care of the sign. Plus, minus, plus, etc. So minus, plus, minus, plus, minus, plus. And we put the minus by, we calculate them by column and we put them by rows. And then either case M equal 2 or case M equal 3, we have our Adjugate matrix. We dot it with, we multiply it by the matrix B containing the images, and we divide by the determinant to get the answer. So very simple. The main difference is calculating the Adjugate matrix and the auxiliary determinants. But as you can see, the same effort, the same number of miners, exactly the same. And here you might say we have an inner product. Here also we have an inner product. If you can see here, this is the inner product of B, B1, B2, B3, the components of B, with the adjugate matrix. This is adjugate matrix, exactly the same. This is the adjugate matrix. Here we have calculated the minors and combined them with vector B to calculate the auxiliary determinant. And we have seen that also in the tutorial. If you remember, let's write it here. The adjugate matrix of A times vector B, one single vector B, is equal to the auxiliary determinant, D1, and D2, and D3. You calculate either directly the auxiliary determinant, or you multiply the adjugate matrix with the vector B, exactly the same. So we have exactly the same amount of calculation, the same accuracy. The two methods are equivalent. You choose Cramer's rule or the adjugate matrix for small matrices, for small matrices, not for large matrices. For large matrices, both are impractical. So for small matrices, you choose Cramer's rule or adjugate matrix, you obtain the same result. But the advantage with the adjugate matrix, it can deal with a set of images using one single matrix. You calculate it only once, and it is the most expensive operation in the algorithm, is to calculate the minus, the adjugate matrix. So let's test it. We test it using the same script we have used to test Gabriel Cramer. We prepare the data. We call our function not Gabriel Cramer, but adjugate matrix. And here we have only one column, because B, the vector B is one column. So here matrix B, let's write it here, matrix B equal one single column B, one single. We test only one single column, but it's okay if the algorithm works for one single column. It works, of course, for the other columns. So let's save it and we test it. So let's try with first system. And as you can see, the solution, the determinant, and the norm of the residual close to zero. Let's test again with 2. We have seen the first and second system, we have seen them in the lecture, in the third and the fourth lecture. Okay. Always check first the norm of the residual. It is close to 0. And number 3, same, close to 0. And if you remember the values we have calculated in the tutorial, in the last video, both with Cramer's rule, directly with Cramer's rule, or using the adjugate matrix. And let's check when the matrix is singular. So it catches that, like Cramer's rule. 8, same. So this is a singular matrix with rank 1. And I think that's it for the adjugate matrix. Let's apply this technique, the adjugate matrix, with several images to solve a concrete problem in geometry. In the third part of this practical, we study a simple problem in geometry, in a plane, in 2 dimensions. So let us suppose we have the axis of the plane, the x-axis, and the y-axis. And on this plane, we have a circle. A given circle, defined by its center and its radius. So XC and YC. And let us suppose there is in this plane a linear mapping. We have defined a linear mapping, a matrix A, invertible matrix, in R2 by 2. And the problem is, let us suppose that the points on the circle, on the parameter of the circle, are images of other points. So there is a shape here in the same plane, the same reference. There is a shape, we do not know it, a known shape, such that its image by the linear mapping A is a circle. Every point on that shape is associated to a point on the circle. We know the image, but we don't know the source. So our problem is to find the source shape. Our problem find the source shape. Because why these images exist? Because the matrix is invertible. Then the image space is the whole plane. Any point or vector position, you can say point or vector position, because linear mapping is between vectors. But you can associate to any point on the plane, you can associate it to a vector. It's a position vector. So any point on the plane is an image of another point, because the image space is the whole plane, the dimension, the rank is equal to. That's why we can consider that if the matrix is singular, we cannot say that. We cannot say that every point is an image. But because A is invertible, every point on the circle is an image. We cannot also deal directly with the shape because it contains an infinity of points. We have to discretize it. We have to choose some points on the circle, and find their sources on the source shape, the source vectors. We have the image vectors, and we are looking for the source vectors. So more precisely, let us suppose there is a family of points from I equal 1 to n. N is the number of points belonging to the circle, defined by the vector position of its center, xc. So here xc is the coordinate, the x coordinate and the y coordinate of the center of the circle, and its radius. So these are given. So given a family of points, on the circle, find the point OM, the family of points, OMI, yeah, I from 1 till n, such that the mapping of each vector OMI is OPI. for I from 1 to n. So we have here actually a system where the unknown is the family of points OMI, and the points on the circle should be given, and the mapping also. So the points are on the circle. For example, this is P1, this is P2, P3, etc., etc. And this is the origin of the reference. So we can write this system in this way, rewrite it in this way. A dot x, matrix x, equal matrix B. Find x, the matrix x, where x is a matrix defined by columns. Each column is the point OM. So OM1, the first column, OM2, the second column, and so on till OMN. So it is a matrix 2 by n. N is the number of points that we have used to discretize on the circle. So for example, here we have 8 points, and here the coordinate of the point, the x coordinate and the y coordinate. So it is a 2 by n. And same for B, each column represents a point on the circle. These are unknown on the unknown shape we are looking to find. So B is the given point on the circle OP1, OP2, etc. till the last point OPN. So this is our system. This is the problem we have to solve. And because we have several images, OP1 till OPN, Cramer's rule is not adequate for this problem. We have to use the Adjugate matrix, and the matrix is very small, so no problem with the performance. So the Adjugate matrix, we have already implemented it, we will use it. But before to do that, we need to find, to generate the points on the circle, because B must be given, must not be an unknown, must be given. So our first task is to generate the family of point OPI, I from 1 to n on the circle. On the given circle, a circle is defined by its center and its radius. We give the center and the radius of the circle, and we have to design and implement a function to generate those points. And the second task is to solve the system. Solve the system AX equal B using our function solve linear system with the version Adjugate, not Cramer. Now the second step, or the second point in this section, is how we generate the points. Generating points on a circle. So first of all, the best way to define points on a circle is to use polar coordinates, and the local, let's use another column, and the local reference whose origin is the center of the circle, not O, not the global reference. This is a local reference. And each point on the circle can be defined by the angle let's call this the point PI, and the angle, the point PI, and the angle, let's call it theta I, and the radius r. So each point PI is defined by its angle theta I and the radius of the circle. So if we know the angle, we know the point, because the radius is common to all the points on the circle. So we have to generate a sequence of angles in order to have a sequence of points. For example, equally distant. So to generate the point PIs, to generate the points PI, I from 1 to n, we use an arithmetic sequence, an arithmetic that is the same step, so equally distant on the perimeter of the circle. An arithmetic sequence. We have seen in the practicals on MATLAB, we have done 7 practicals. The 2 first are on matrices. And you can check them if you have forgotten. We can use linspace to generate an arithmetic sequence. We know the beginning and the end. We don't have to give the step, we give the number of elements in the sequence. So we use a linspace, a built-in function, linspace. We give the start is 0, the point that should be here, first point, and the last after 2p. It should normally here before a given angle, but we don't know the angle. So I give the same point, but with a different angle. So the point with the angle 0 and the point with the angle 2p coincide. They are the same point, but the angles are different because it will cycle. After each 2p, you get the same point. So we will eliminate it later. So we do 0 and 2p, or 2pi, p in French, 2pi, and the number n of points. And we put that in t. Or because theta and p are not possible to code in MATLAB. MATLAB deals only with ASCII letters. So we call it the vector t. Here we write p, yeah? Let's write it like that. Pi, I mean. Pi in MATLAB is a constant equal to p, to pi. So Greek letter doesn't work in coding. So we get all the points, and the last point is extra. We eliminate it. We eliminated the end. We eliminate it by assigning to it an empty vector. So we eliminate the last point, and we get the vector t should be 2p over n, 2p over n, and 0, 1, 2, etc. till n minus 1. So we have n points. If you count, we have n points. We have eliminated the point n because when we multiply n by 2pn, we get 2p, 2pi, I mean. 2pi and 0 are the same point. That's why we have eliminated it. The point that should be here, we have eliminated it. And here, if we want n here, we have to add plus 1. So here normally it's not normally, there's an error. Should write here n plus 1. We have our points in polar coordinates. So this is the polar coordinates. Polar coordinates in the local reference. A local reference means the center of our, the origin of our reference is the center of the circle. Okay, see. Now what we will do, we transform these coordinates to the Cartesian coordinates, because our mapping is on the axis x and y, on the Cartesian coordinates. How we do that? So the second is Cartesian coordinates. How we can use, of course, we can use cosine and sine. We can use the triangle here with the right angle. This is the x coordinate, and this is the y coordinate of P. Let's say Py and Px. This is the point P. We can do that, of course, and use the angle theta, and write that is r cosinus, and this is r sinus. We can do that. R sinus, r sine, I mean theta, and Px, r cosine theta. And use the function sine and cosine, but it's better in MATLAB to use a built-in function dedicated to this problem, to transform the polar coordinates to the Cartesian coordinates, called pole to carte. Pole to carte. And pole to carte, you should give the angle theta and the radius, the length of the hypotenuse. And you get Px and Py. You can do that for one single point or for a sequence of points. In that case, you get here a row vector and a column vector. I mean a row vector for x and a row vector for y, if theta is a vector. So that's exactly what we will do here. We write Px, the vector Px, and the vector Py is equal pole to carte, a built-in function. So we don't have to reinvent the wheel and implement sine and cosine, etc., loop 4, etc. We don't need that. We just call pole to carte, and we give it the angle. For one single point, you have to give a number, of course, but for several points, you have to give the vector t that we have generated using green space. So the vector t and the same radius for all the points. And here it is a row vector, not a column vector. So we should get here Px and Py like that. There are row vectors, Px and Py, row vectors. So there are one row by n columns. And then we transform the Cartesian coordinates from the local. This is the local. This is the local reference to the global reference. So the third, from local to global reference. we have the local reference and the global reference. This is O, and this is C. Any point here on the circle. Any point P on the circle. So, the global position of P is OP. It is equal to OC plus CP. This is the local position, and this is the global position. So what we do, we simply store these coordinates in a matrix and add them to each column, the position of the center of our circle. We add this vector. Which is the position of the center of the circle. So we call the matrix OPS, the position of all the points. We get the PX in the first row, and PY in the second row. We use a semicolon, because the first row and then the second row. Otherwise, it will be one single row, a long one single row. So PX, first row, semicolon, and PY. And we add the position of the center. Or visually, we get like this. This is 2 by n, and we add the column vector containing the coordinates of the center. The position of the center must be stored in a column vector. Otherwise this will not work. Normally, this is an element-wise operation, as we have seen in the practicals on MATLAB. When you use element-wise operation, the two matrices must be of the same size, the same number of rows, the same number of columns. But there is an exception when you add a column by column. So this column will be added to every column of the first matrix. So this is, or you can of course commutate. It's commutative. And we store that in the matrix OP. So the matrix OP contains the Cartesian coordinates of all our points. Of all our points we generated on the circle. So 3 steps. We generate a sequence of angles using lean space that define the polar coordinates of our points on the circle. Then we transform them to Cartesian coordinates in the local reference, still in the local reference, but with Cartesian coordinates, that is the x and y, using pole to cart, polar to Cartesian. And we store the result in 2 row vectors. And then we transform the Cartesian coordinates from the local to the global reference, by simply putting the row vectors in a matrix. The first row of the matrix is the x coordinates, and the second is the y coordinates of the points. And we simply add the position of our center. Very simple. 3 steps. Let's see, before to see that on the computer, let's give it a name. The function, let's call it, we have called it genCirclePoints. Circle points. Function genCirclePoints. Let's see that on the computer setting. Our function genCirclePoints in a file with the same name, and the input xc, a vector containing the coordinates of the center, the radius r, and the number of points on the circle. The default value is 50. And if we omit n, it is set to 50. and the matrix OPS containing the coordinates of the generated points by column. Each column is a point. So let's read the comment. Generate a finite set of points on a given circle, Tahar Scholar channel, module numerical methods as a first course, chapter 2, systems of linear equations, implemented by Tahar Jawad, Tuesday, the 20th April 2024, and by the Algeria, the input XC, R, and N, and the output OPS. I read intentionally the first comment for copyright reason. So, to emphasize, I'm the author. And also the date is important. So the first step is to check the data as usual. We make sure that XC contain only two elements, the components of the coordinates of the point, that R is positive, and N is a positive integer. Its whole part or integer part is equal to the number itself. And then we check if XC is a row vector. It must be a column vector, but if it is a row vector, we transform it to column vector, so that the function accepts XC to be row or column, but in the code, it will be always a column vector. So now we implement what we have seen in the notebook setting. We generate a sequence of angles using lean space. It starts with 0 and ends with 2 pi. And we give one plus point, an extra point, the point with the angle 2 pi, because it will coincide with the one with angle 0. And then we eliminate it. And our sequence will contain only n points, not n plus 1. And then we transform the polar coordinates to Cartesian coordinates using pol2cat, and we store the result in px and py. The x coordinates and the y coordinates in two separate. We cannot use a matrix here because we have to follow the header or the implementation of pol2cat. Pol2cat tells us to put the x and the y coordinates separately into row vectors. Then we gather them in a matrix. The first row for the x coordinates. The second row we use a semicolon. Be careful here. We use a semicolon. So the first row for the x coordinates, the second row for the y coordinates, and we add the coordinates of the center to each column of the points, and we get OPS. Very simple. Let's, before to use this function in our project, let's test it. Let's go to the command window, and let's generate OPS for 8 points. So gen circle and XC, let's say 3, 1. So x coordinate is 3 and the y coordinates is 1. And the radius 2.5. For example, you can change, of course, and choose any value you want. And 8 points. And we enter. So we have the matrix here. This is the first point. The x and the y the first point. The x coordinate and the y coordinate for the second point, and so on. We have 8 points. The points are stored by columns. And let's draw that. We use plot to visualize it. OPS, first row for the x coordinates and the second row for the y coordinates. And we plot them in red color, marker O, and the line joining the points. So let's enter. Okay. Now that here, let's add axis equal and grid on. And see the figure again. Okay. So as you can see here, we have generated 8 points. 1, 2, 3, 4, 5, 6, 7, 8 in the anti-clockwise direction, or trigonometric direction. So the center of the circle, 3 and 1. In the global reference. This is the axis, the x-axis, and this is the y-axis of the global reference. So let's come back to our project. I have implemented the script in project Geom, and see, it's very simple, very easy. We prepare the data for the system. We call the function solve system adjugate to solve it, and then we plot the result. Let's read it. Let's read first the comment, or the comments. Find the source set of points whose images according to a given linear mapping are a given set of points carried by a circle. Tahar Scholar Channel, Numerical Methods as a first course, and Chapter 2, Systems of Linear Equations. Implemented by Tahar Jawad, Tuesday, 20th April 2024, and by the Algeria. We clear all as usual, CLC, and we prepare the mapping. We need a matrix, an invertible matrix. I have chosen the matrix we have seen in lecture 3 when we presented Cramer's rule. Then we generate, we need not just the mapping, we need the points on the circle. So we call genCirclePoints with the same as in the previous example. You can change, of course. You choose what you want. You can change also here. It must be invertible, and you can play with the input. So this is the coordinates of the center and the radius. We do not need any. It will generate 50 points, and we store that in the image matrix, the matrix containing the image vectors by columns. And then we call the function solve system adjugate to solve our problem. The input is the matrix, and the matrix B, and we get the source vectors in the matrix X. We check if X is empty. This case could happen if you have mistakenly given a singular matrix. If the matrix is singular, then X will be empty. The function. What is the function here? Yes. The function initialize X to be empty. If the determinant is close to 0, X will be empty. That's why I check if X is empty, the system, I display an error. We display an error message, the system matrix is singular. And we stop the code, of course. Otherwise we continue. So we have in X, the points, the source points, whose images are stored in B. So we draw them. We draw them on a subplot. This might be a little bit complex, but it's very simple. We need to draw both the image and the source points. We use subplot in a grid, one row, 2 columns, and in a loop we set each axis. Because here we have 2 axes. We cannot use hold on, grid on, alone like we have did in the command window. Like we have did here, axis equal and grid on. Axis equal and grid on is for the current axis, for the current graphic axis. But when you have a subplot, you have to do that in this way. You give the handle. So subplot will return a handle depending of the index you have. For I equal 1, it gives the handle of the first axis. For I equal 2, it gives the handle of the second axis. And we store this handle in big H. Big H contains 2 elements. The first is the handle for the first axis, and the second element is the second handle, or the handle of the second axis. So we store the handle of axis in big H. And then we call hold and the handle of the axis. So we apply hold on for the first axis and the grid on for the first axis and axis equal for the first axis. And then we loop for I equal 2. We repeat the same for the second axis. Hold on, grid, and axis. And then we plot the x coordinates and the y coordinates of all points in B, and same of all points in X. But here we plot in the first handle, using the first handle, the first axis, and here in the second handle, the second axis. And we use different color, red for the image and B for the source. So, very simple. So let's test it. So we have here the figure. This is the circle, the input. All the points generated on the given circle. The center is 3 and 1, and the radius is 2.5. These points are the images of this one. So our source shape is an ellipse. All these points are mapped to a circle. And you can actually change, this is a general result. You can change the matrix, the input matrix, play with the matrix, any matrix, but it must be invertible. 2 by 2 matrix, invertible. You will always find an ellipse. The source shape is always an ellipse. Of different, of course, orientation and size, but always the same circle. If you change the mapping, you will always find you will find an ellipse, and vice versa. If you take a source, a circle, the image will be an ellipse. This is a property of linear mapping, because linear mapping will will translate a vector or rotate it. So that's why the shape will actually not change. Circle is a particular case of an ellipse. It's a special case of an ellipse. So that's it for the third part. Let's move to the fourth and last part, time complexity. In the fourth part of this practical, we discuss the performance of the two methods, Cramer's rule and the Adjugate matrix. We have already seen Cramer's rule and the Adjugate matrix in lectures, in tutorials, and in this practical we have seen how to implement them for small matrices. Now we want to discuss their performance, their time complexity. So the two methods actually are related to each other, are equivalent. If you remember the relationship between the Adjugate matrix of A and the auxiliary determinants. When we do the inner product of the Adjugate matrix with the image vector, we get the auxiliary determinants, delta 1, delta 2, etc. until delta n, where delta I represents the determinant of the matrix with vector B at the ith column. So from I, from 1 to m. So these are the auxiliary determinants. This is Cramer's rule. Auxiliary determinants used in Cramer's rule. In Cramer's rule. And this is the Adjugate matrix used to calculate the inverse of the matrix. The Adjugate matrix. So the two methods are actually equivalent. What you do in the Adjugate matrix, you do it in Cramer's rule, and vice versa. Now, we would like to formally compare the two methods. If you remember, so let's say this is the first point. If you remember, in lecture 2, when we have done a revision on matrix algebra, we have seen that for a determinant, the time complexity of a determinant, to compute a determinant of a matrix, of an m by m matrix, is in the order of m factorial. flop. Flop, not flops. Flop mean floating operations. It's plural, but without S. With S means floating operation per second. That's the time needed by computer to perform floating operations. But here we are not concerned about time, but the number of floating operations. How many floating operations we need to compute the determinant? It's in the order of n factorial. Order of n factorial means it's a lower bound. There are other terms, negligible when you compare them to n factorial. So the dominant term is n factorial. For example, for m equal 5, the order is 5 factorial, 120. So just for a matrix 5 by 5, you need 120 floating operations, at least 120 floating operations. So it's a huge chance. That's why it is impractical for large matrices. But let's use that, this fact, it's a theorem, this property to calculate or to estimate the time complexity of the adjugate matrix and then of the auxiliary determinants. So let's do that like this. Here, the adjugate matrix. So let's suppose we have a matrix. So we have here a matrix 5 by 5, m by m with m equal 5. And we want to calculate the adjugate matrix. The adjugate matrix, as we have explained before, it is related to the minors. You calculate the minors. You calculate them by columns, and then you put them by rows. So we have to calculate the minors of each element. We calculate m square. How many elements here? We have m square, m by m. M square minus of order m minus 1. So we calculate actually the determinant of a submatrix of size m minus 1. And we do that m square times. What is the time complexity of a minor of order m minus 1? We have just seen that determinant of an m by m matrix needs O m factorial. So here we need O m minus 1 factorial. For each determinant, for each minor, we need m square minus, the minor has a time complexity of m minus 1 factorial, and we have m square, so we just multiply times m square. That's the time complexity to calculate the adjugate matrix. So let's write it here, flop. When we multiply m by m minus 1, what do we get? We get m factorial. So this is equal to m times, because O m factorial is a constant, and m minus 1 factorial. The constant is independent of m. So when you multiply m by m minus 1 factorial, you get, of course, m factorial. So it's in the order of m factorial. That's the time complexity to calculate the adjugate matrix. And now for the auxiliary determinants. The auxiliary determinants. Determinants. So let's say we have a matrix A, like here, m by m, and one column, we replace one column with the vector B to calculate the determinant. Here it's the second auxiliary. So here it's the second auxiliary. We are looking for its time complexity, there are m auxiliary determinants, delta 1, delta 2, etc. So let's focus on one. For example, delta 2. How we calculate it? How we calculate the determinant delta 2? We cross the column containing B, element by element, and for each element, for example, for this element, we eliminate the row and the column, and we get a submatrix of order or of size m-1. So the first thing to do, for each element, we calculate a minor of order m-1. That is for each element. So we have m element in the column. So we have m times the order of m-1 factorial. So, but we have also to multiply. We multiply. When we calculate the minor, we multiply it by the element. Then we multiply it by the element. We have to calculate B1, M, we are in the second column, so 1, 2, and minus. Then plus B2, M2, second column, minus B3, M3, 2, always the second column, etc. The sign alternate, and always we have a minor here of order -1, etc. until Bm, or the sign here is -1, the column is 2, and I is 2, the number of rows. So m plus 2, the sign. It can be plus or minus. And then Bm, the element, and then the minor. This is the definition of the determinant. We are calculating the determinant delta 2 and m2. So we moved from the first row, second, third, until the mth row, always in the second column. We have seen the time complexity of each minor, and we calculated it's m times O m-1 factorial. But we have to do here multiplication. The element, the minor. Now the element times the minor. The elements times the minor, and so on. We have m. So besides this time complexity, we need also m multiplication. Plus m-1 addition, we have to add, plus or minus. If you have two elements, we have only one addition. If you have three, we have always, it's the number of elements -1, because the addition goes by pair. So we have m-1 addition. Let's write it like this, addition. So the total will be m times O m-1 factorial. So m O m-1 factorial for all the minors in the determinant, plus m and m-1, that is 2m-1 floating operations, flop. For delta I. So we have picked one determinant, but it's the same reasoning for any auxiliary determinant. So this is only for one auxiliary determinant. And that's why for all delta I from 1 till m, we need this term, m O m-1 factorial plus 2m minus 1 all multiplied by m, by the number of auxiliary determinants. And we get, when you multiply m by om minus 1 factorial, that's om factorial. And m by 2m minus 1 is 2m squared minus m. So we get m o m factorial plus 2m minus 1, 2m minus m, 2m squared minus m flop. That's the total cost of all the auxiliary determinant. Let's now consider the method. We have considered the most expensive operation in the two methods. Now let's summarize all the steps in each method. So in the adjugate matrix, we need first to calculate the determinant, delta, the determinant of the main matrix. Its time complexity is OM factorial, like any determinant. Then the adjugate matrix of A, we have just seen its M OM factorial. And this is the most expensive operation in the method. And then we perform the inner product, the adjugate of A dot the image vector. If you see here, let's draw here. So when we do the inner product, we multiply the elements in B with the first row to get the first element of the vector. This is a vector. So we multiply the elements in B by the elements of the first row, and we add. So we have M multiplication for the first row. We have M multiplication and M minus 1 addition. That is 2m minus 1 for the first row. And we have m rows. So for all the rows, it's 2m minus 1 times m. That is 2m squared minus m. So the time complexity here in the inner to perform the inner product is 2m squared minus m. This is much less expensive as m factorial, because m factorial gets very large, quickly very large. Even for 7, 8, 9, it gets very large compared to m squared. So, and finally we calculate our solution, which is the vector inner product RGA dot B. This is a vector containing m element, and we divide it by delta. Each element we divide it by delta. So we have division m times. So we have m flops, m flop, m flop, and then that's it for the adjugate matrix. Let's count. We have m plus 1, so the total is m plus 1 OM factorial plus 2m squared minus m plus m. So we get OM plus 1 factorial plus 2m square flop. This is the total cost in the method of the adjugate matrix. This is the dominant term, m plus 1 factorial. Okay, let's now do the same with Cramer's rule. We first also calculate the determinant of A, and the time complexity is O n factorial. Then we calculate all the elements in the family delta I from 1 to m, the auxiliary determinants. And we have seen just before that it is m time complexity. The time complexity in this step is m O m factorial plus 2m square minus m. This is the most expensive operation in Cramer's rule, is to calculate the auxiliary determinants. And the dominant term here is, of course, O n factorial. And the third step is to calculate the solution, the x. Here we subdivide each auxiliary determinant by delta, by the main determinant. So we have a vector containing all the auxiliary determinants, and we divide it by delta. Division is an operation. How many times? M times. So we have m flop. You can observe here, when we compare the two most expensive operations, this is more expensive. Calculating the auxiliary determinants is more expensive than calculating the adjugate matrix. But then we have to do the inner product. And the inner product, as you can see here, is the same as this second term. So actually, the inner product of the adjugate matrix with the image vector, along with the adjugate matrix, have the same time complexity as the computation of the auxiliary determinants. So they are the same, exactly the same. Let's do the total. We have m plus 1 O m factorial plus 2m square m minus m plus m. We eliminate and we get m plus 1 O m factorial is O m factorial, O m plus 1 factorial. We get exactly the same time complexity. So the two methods are actually equivalent. You solve small, for large systems it's impractical for both methods, but for small matrices, you calculate the solution, compute the solution using the adjugate matrix or Cramer's rule are exactly the same. Computationally and even for the accuracy, it's the same technique. You calculate minus. Basically, it's calculation of minus from order m minus 1 till 1. There is a scenario that we have seen already in the practical when we done the project Geom. When you have several images with the same matrix, then the adjugate matrix is better, because you calculate the adjugate matrix only once. It is separated from the images, while here the vector image is embedded in the auxiliary determinants. So let's summarize. Let's give an example. For example, m equal 5. We have the time complexity is for the first term O6 factorial plus 2 5 square. We get for the first term 720, and the second term 50. So the dominant term is OM plus factorial, and we get 770 flop, floating operations, flop, for m equal 5. So even for a small matrix, like this one, 5 by 5, we have to do 770 flop. It's very, it's time consuming with hand computing. With a computer, it's nothing. But with computers nowadays can perform 1 teraflops per second. So it's nothing for a computer. But for hand computing, it's really consuming time. So let's summarize here. Both Cramer's rule and the Adjugate Matrix have a time complexity of OM plus 1 factorial. Well, the determinant is only m factorial, but the method to solve, you need m plus 1 factor. To solve a system is m plus 1, you add 1, m plus 1 factorial. This is the most dominant term. The other, we can neglect it. When m get large, we can neglect the square before m plus 1 factorial. So have a time complexity of OM plus 1 factorial for a matrix, for an m by m matrix. And that's it for this practical. It's a little bit long, but this is the end for this first part, Cramer's rule and the Adjugate Matrix. Next time, inshallah, we will see Gaussian elimination. We come back to lectures and study the Gaussian elimination. See you then in the next video, inshallah. Peace.